Hey there, it's Shannon Matchick-Myers, and today we'll be looking at the rank and nullity of a matrix, systems of linear equations, yet again, and coordinate vectors. So let's get started by doing a few math stretches. Let's look at this matrix A equal to 1, 3, negative 1, 5, 7, 1, 13, 6. The row vectors of A are what? Beautiful. One of the row vectors would be, we called this row vector 1, row vector 2. We would have row vector 1. You can write it one of two ways. You could write it as a vector in component form. So you'd have 1, 3, negative 1, and 5 with commas in between the components. Or you could write it how? Beautiful. As a 1 by 4 vector. And then row 2 would be either 7, 1, 13, 6, or we would have the 1 by 4 matrix, 7, 1, 13, 6. Cool? What about the column vectors? Beautiful. Column vectors, so we're going to have 4 column vectors. Because there's 4 columns. And I really like to write the column vectors as actual columns in matrix form. I find that this helps clear up confusion when we're learning about different things like null space and column space and row space. So I'm going to write it like this. So our first column would be 1, 7. And then column 2 would be 3, 1. Column 3 is negative 1, 13. And column 4 is 5, 6. Cool? All right. You feel all warmed up? Very good. Now, the definition of row space and column space of a matrix is as follows. Let A be an M by N matrix. The row space of A is the subspace of Rn spanned by the row vectors of A. So remember, if you have an M by N matrix, N represents the number of columns, and so you would have a row vector with N components. The column space of A is the subspace of R, and this should be M. I'm sorry about the typo here. Rm spanned by the column vectors. Cool? All right. So notice here, all right, when we went back to our warm-up here and we just looked at the columns, these aren't necessarily the spaces by any means, but you can get a feel for it. Notice that A had dimension what? 2 rows, right, by 4 columns. So to kind of clear up any confusion about the Rn and Rm stuff, notice that for our row vectors, we had 4 components in the row vectors. So, and that's because there are 4 columns that are represented in each row, right? So you have to have 4 entries in your row vectors. Whereas in the column vectors, okay, you have it is true that you have 4 columns, but each of the vectors has 2 entries, right? Because you have 2 rows. Cool? Okay, so a lot of times people confuse that a little bit. Now, recall that 2 matrices are row equivalent when one can be obtained from the other by elementary row operations. So this brings us to our next theorem, 3.12. Row equivalent matrices have the same row space. This is a super important concept. If an M by N matrix A is row equivalent to an M by N matrix B, then the row space of A is equal to the row space of B. So to show equality, what we need to do is show that each of the spaces are subspaces of each other, okay? So here we go. Let's do it. First of all, why don't we use the fact that since A is row equivalent to B, so remember, row equivalence means that you've got to have a finite number of elementary matrices where you can write B as the product of those elementary matrices in descending order times the matrix A. So let's write that out in words. So we have there exists a finite number of elementary matrices let's denote them E1, E2, all the way down to E sub k, such that B can be written as the product E sub k times E sub k minus 1 all the way down to E2 times E1 times A. All right, well, from this, it follows that the row vectors of B can be what? Beautiful. Can be written as linear combinations of the row vectors of A. All right then, well, the row vectors of B what can I say about them? Beautiful. They're going to lie in the row space of A. And what else? The subspace spanned by the row vectors of B is contained in the row space of A. So what we've shown here is we've shown that the row space of B is a subspace of the row space of A. Okay? So similarly, you can go through the whole thing again, and it's really the same proof, just switched around a little bit. The row vectors of A lie in the row space of B and the subspace spanned by the row vectors of A is contained in the row space of B. So we've just shown that the row space of A is a subspace of the row space of B. And that's what we needed to do when you show that two sets or two spaces or subspaces of each other. You've shown that they are equal. So therefore, the two row spaces are subspaces of each other. Thus, the row spaces are equal. Cool, cool? All right. So our next theorem is called the basis for the row space of a matrix. If a matrix A is row equivalent to a matrix B in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. Okay, so here's how we do it. To find a basis for the row space of a matrix, row reduce the matrix. The non-zero rows in the reduced matrix are a basis for the row space of the matrix. Your answer should be in the form of a set of row vectors. Now, it's very important that you use, if you row reduce the matrix to find this, then you need to use the rows from the reduced form, not the rows from the original matrix, because you don't know which row is zeroed out. Okay, unless you were doing it by hand, and most of these will just use technology. To find a basis for the column space of a matrix, there's a couple ways you can do it. You can use the steps above on the transpose of the matrix. Your answer should be in the form of a set of column vectors. And again, in this method, you need to use the column vectors from the reduced matrix. The other method is just to use the aria form of the original matrix A, and then you find the columns that contain the pivots. Remember, the pivots are the leading ones. You use the corresponding columns from the original matrix. You need to use it from the original matrix in this one for a basis. Your answer should be in the form of a set of column vectors. Cool, cool? All right. So let's do it. Find a basis for the row space and column space of the following matrix. So we have A is equal to 2, negative 3, 1, 5, 10, 6, 8, negative 7, 5. All right, so to find the information about the rows, we have 3 rows contained in the reduced row echelon form, and one of them is a row of zeros. So you don't use that one. What you do is we're going to use rows 1 and 2 from the reduced row echelon form of A. So here we go. A basis, remember it's not the basis, it's a basis for the row space of A is going to be 1, 0, 4/5, and 0, 1, 1/5. Good so far? Awesome. All right. So 2 different ways we can go about finding a basis for the column space, right? So if we use method 2, what would we look for? Well, column 1, column 2, and column 3 here in the reduced form. And do you see that the pivots, the columns that have the pivots, the leading ones, are column 1 and column 2. And these are the pivots right here. And so remember, you have to go back over here to the original and use the columns that contain the pivots in the reduced row echelon form of the matrix A. Good so far? So using method 2, a basis for the column space of A, and we'd have the set that contains the 3 by 1 matrices, 2, 5, and 8, and then negative 3, 10, and negative 7, and that came from the original matrix A. Cool, cool? All right, so that is one way of doing it. The other way would be to hit second entry. We've got RREF of A, but I want RREF of A transpose. So if I do second matrix math transpose, and then I find this, and I want to see if I can put this in form of a fraction, so I'm going to hit math fraction, enter. So here we go. 1, 0, 23 sevenths, 0, 1, 2 sevenths, and the others are zeros. So what we need to do is this. We need to take the rows, right, of the reduced form that do not zero out, and then transpose them. So we'll use this row and this row, right? But we've got to write them as our column matrices. So we will have, using method 1, a basis for the column space of A will be 1, 0, 23 sevenths is a column. Remember, you have to use the reduced form. And then 0, 1, 2 sevenths. All right? Okay, perfect. So here we go. For example 2, find a basis for the row space and column space of the following matrix. So what I'd like you to do is pause the movie and see how you do. All right? On to the next one. Theorem 3.13, row and column spaces have equal dimensions. So if A is an m by n matrix, then the row space and the column space of A have the same dimension. Remember, how did we find dimension before? Dimension of, some space. Good, we counted the number of vectors that were in a basis for the space. Well, look what happened here. For both these problems, 2 vectors in the basis for the row space of the matrix A in the first example, and 2 vectors in a basis for the column space of A. And then again, example 2, 2 vectors in a basis for the row space of A, and 2 vectors in a basis for the column space of A. So that tells us, this theorem tells us that they always have equal dimensions. Now, the definition of the rank of a matrix, the dimension of the row or column space, because they have the same dimension, of a matrix A is called the rank of A, and is denoted by just rank of A. Okay? All right, well, we already looked at that. Find the rank of the matrix from example 1. Wasn't it 2 in both cases? Because there's 2 vectors in the row space or the column space. So for each of these, we get 2. All right. Now we get into theorem 3.14, solutions of a homogeneous system. If A is an m by n matrix, then the set of all solutions of the homogeneous system of linear equations, A times the vector x is equal to the 0 vector, happens to be a subspace of Rn, called the null space of A, and is denoted capital N at A. So the null space of A is equal to the vector x that belongs to Rn, such that A times the vector x is equal to the 0 vector. Cool, cool? The dimension of the null space of A is called the nullity of A. All right, let's do the proof for this one. So since A is an M by N matrix, X, that vector X, has to have what size? Beautiful. N by 1. So the set of all solutions has to be a subset of Rn. Cool, cool? All right. So what do you think we're doing? We're doing the proof for a subspace, right? So we've said that this is a subset of Rn, right? This X vector. And what do we also know? This set has to be non-empty, since the trivial solution always works, right? A times the 0 vector is equal to the 0 vector. All right? So we have a non-empty subset. So we have to show closure under addition and scalar multiplication. Well, let's check it out. If we look at A times the sum of these two vectors, that's going to be what? We know that the multiplication is defined, so it would be A times x1 plus A times x2. But what do each of those have to equal to? Beautiful. It's got to equal to the 0 vector plus the 0 vector, which is equal to the 0 vector. So we have closure under addition. All right, how about A times a constant times a vector x1? Well, what would that equal to? Beautiful, we can bring the constant out and have the constant times A times x1. But what is that equal to? Beautiful. C times the 0 vector, which is going to give us the 0 vector. So A is closed under scalar multiplication. Therefore, A times x equal to the 0 vector is a subspace of Rn. Cool, cool? Alrighty. Next up, let's find the null space of the following matrix A and then determine the nullity of A. Cool so far? So we've been given this matrix A. What size is A? Beautiful. 3 by 4. So the vector x has to be of dimension, you got it, 4 by 1. And why don't we just call x, x1, x2, x3, and x4? Cool, cool? And we're working with the equation A times x is equal to the 0 vector, right? So How do we do that one? Remember, there's a couple different ways. You could just find the RREF form of A and then just recognize that you have a column of zeros, right? Or you could, just to be on the safe side, so you don't lose any of your dimension stuff, you could have 1, 4, 2, 1, 0, 0, 1, 1, negative 1, 0, negative 2, negative 8, negative 4, negative 2, and 0. So then you could row reduce this guy. All right, so let's see what that gives us. We would have x1 minus 2x3 plus 5x4 equals 0. x2 plus x3 minus x4 equals 0. And then the other one is just 0 equals 0. So what does that give us? Well, if I isolate x1, I would have 2x3 minus 5x4. And if I isolate x2, I'll have negative x3 plus x4. And if I were to let x3 equal to s and x4 equal to t, what will we have? x1 will equal to 2s minus 5t. x2 is going to equal to negative s plus t. And then, like we said, x3 was s and x4 was t. Now, this is where we want to kind of put things together here, all right? So, what do we know about the vector x? Well, it equals to x1, x2, x3, and x4. But what did we find for that? We found that this was equal to 2s minus 5t, negative s plus t, s and t. Cool so far? All right, now I'm going to split these vectors up into a sum of two vectors. So I can write this as 2s, and then the next vector would have to be what? Minus 5t in that first spot. And then coming back, we'd have negative s, and then in the next vector, we'd have plus t. And then we would have what? An s and a 0, and then a 0 and a t. Cool so far? So putting it all together, if we were to factor out an s from the first one, we would have 2, negative 1, 1, 0. And then if we factor out a t in the second one, we'd have negative 5, 1, 0, 1. Groovy? So at this point, you can let s equal whatever you want and t equal whatever you want. So here, a basis, so if we let s equal t equal to 1, a basis for the null space of A is the two column vectors 2, negative 1, 1, 0, comma, negative 5, 1, 0, 1. Cool, cool? All right. And that's what we wanted to find. What about the nullity of A? Well, there are two vectors in a basis for the null space of A, so beautiful. The nullity of A equals to 2. All right. Theorem 3.15, dimension of the solution space. If A is an M by N matrix of rank R, then the dimension of the solution space of A times X equal to the 0 vector is N minus R. That is, N equals the rank of A plus the nullity of A. Cool, cool? All right, so example 5. Consider the following homogeneous system of linear equations. Well, x minus y equals 0 and negative x plus y equals 0. That's definitely homogeneous. So find a basis for the solution space. Well, A equals 1, negative 1, negative 1, 1. X has to be what? 2 by 1, right? So we'll just name it x and y, like the variables it already has in there. So what's our REF of A? Well, actually, this one we could do by hand. I mean, if we just added row 1 plus row 2 for a new row 2, what do we get? Beautiful. We'll have 1, negative 1, and then we'll have 0, 0. And what does that mean? That means we're going to have x minus y is equal to 0 because of the fact that we have a homogeneous system, right? So that means that x is equal to y. Cool so far? So if we let y equal to t, then x will also equal to t, correct? So let's see what we have. So we have the vector x was equal to the vector xy, which is equal to t. Now, if we factor out the t, we'll just have 1, 1. Cool so far? So a basis for the solution space is what? Is just going to be 1, 1, because I let t equal to 1 there. Okay, so next up, find the dimension of the solution space. Well, there's one vector and a basis for the solution space, so this is really the nullity of A, right? Because we had a homogeneous system, and that's going to equal to 1. Okay. Find the solution of a consistent system, A times x equal to the vector b in the form of x particular plus x homogeneous, right? So here, well, how could we look at this? Well, if we have A times x equal to some b, right? Then we'd have x would equal to something plus the solution for the homogeneous. And what did we get? We got t times 1, 1, right? Well, What's the particular one that will always work? Beautiful. 0, 0, correct? So this one would be our XP, and this one is our XH. And we're keeping the T there because we want all possible answers. Cool so far? So that is this, if we let T equal to 1 now, then what would we do? We'd have 0, 0 plus 1, 1. Groovy? Solutions of a non-homogeneous linear system. This is the official theorem for our very last part of our last problem. If XP is a particular solution of a non-homogeneous system, A times X equals B, then every solution of this system can be written in the form X equal to X particular plus X homogeneous, where X homogeneous is a solution of the corresponding homogeneous system. Notice it says A solution. To the homogeneous system, A times X equal to the 0 vector. So let's look at the proof for that. If we let X equal or be any solution of A times X equal to B, so that's in our premise, well, then wouldn't X minus X particular, wouldn't that be a solution to A times X equal to 0? So what are we going to have? We're going to have A times X minus XP is going to have to equal to 0, just plugging it in. So I'm plugging in this quantity in for the X. And what does that give us? That gives us that A times X minus A times XP is equal to the 0 vector. But what is X? Isn't X a solution of A times X equal to B? And X particular is a solution to A times X equal to B. So we'd end up with B minus B equal to the 0 vector, right? So if we were to let XH equal to X minus XP, hence, what do we have? Beautiful. X equals XP plus XH. Cool, cool? All right, so here's another theorem. Solutions of a system of linear equations. The system A times X is equal to B is consistent if and only if B is in the column space of A. All right? All right, well, let's take a look. What would we have? We would have A times X would equal to, no, A is M by N, right? So we'd have A11, A12, all the way down to A1N, and then A21, A22, all the way down to A2N. And then going down this way, we'd have A M1, and then A M2, stretching across to A M N times, so for our vector X, we'd have X1, X2, all the way down to Xn. Groovy? That's just A times X. Well, what is this equal to? Isn't this equal to x1 times the first column of coefficients? So a11, a21, all the way down to am1 plus x2 times a12, a22, all the way down to am2, and it would keep going in this fashion until we got to xn times a1n, a2n, all the way down to amn. And so what have we done? We have written a times x as a linear combination of the column vectors, right? So what does that mean? A times x equal to b if and only if b equal to b1, b2, all the way down to bn is a linear combination of the column vectors of A. So that is, the system is consistent if and only if, what? Beautiful. B is an element of what? The subspace Rm spanned by the columns of A. Pretty groovy, huh? All right, so that's it for this proof. And so now we have another example. So we've got this non-homogeneous system of linear equations, right? We want to determine whether A times x equal to B is consistent. So, all right, let's take a look at the reduced row echelon form of this augmented matrix. So we're here, what are we doing? We're finding a particular solution, okay? So let's go to our technology and find the reduced row echelon form of this matrix. So let's see what we have. We have x minus 2y equal to 4, and then z is equal to 0. So x will equal to 2y plus 4. Cool, cool? And if we let y equal to t, then x will equal to 2t plus 4. So for our vector of solutions x, that will be equal to 2t plus 4, 0, 0, which is equal to, so I want to make this into a sum of a particular solution and a homogeneous solution. So we'll have 4, 0, 0 plus 2t, t, and 0. Cool so far? And then if I factor out that t, I'll have the 4, 0, 0 staying the same plus t times 2, 1, 0. I was able to write the x vector in terms of what? The linear combination of the column vectors of A. And so A times X equal to B in this case is consistent. Cool, cool? Okay, so if the system is consistent, write the solution in the form of x equals xp plus xh, where xp is a particular solution of ax equal to b and xh is a solution of ax equal to 0. Well, here we go. X is equal to the 4, 0, 0. If I were to let t equal to 1, then I would have what? Beautiful 2, 1, 0. And so this is my xp, and the second one is my xh. And this is a solution. There's infinitely many solutions. This is just one of them. All right. Next up, coordinate representation relative to a basis. All right. Let B equal to the set of vectors, vector 1, vector v1, vector v2, all the way down to vector vn. Be an ordered basis for a vector space V, and let X be a vector in V such that X is a linear combination of the vectors in V. So C1 v1 plus C2 v2 plus dot, 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 all the way down to Cn vn. The scalars C1, C2 down to Cn are called the coordinates of X. The vector X relative to the basis B. The column matrix or coordinate matrix of X relative to B is the column matrix in Rn whose components are the coordinates of X. So this is the notation, all right? So this is the coordinate matrix of X relative to the basis B. And that's going to equal to C1, C2, all the way down to Cn. So what you have here is that coordinate matrix of X relative to B are just the scalars that are the multipliers to each vector in the linear combination, right? Note, in Rn, column notation is used for the coordinate matrix. For the vector X equal to x1, x2, all the way down to xn, the xi's are the coordinates of X relative to the standard basis. So sometimes it's a so easy, it's hard thing. The standard basis S for Rn. So you have the coordinate matrix of X relative to the standard basis S would just equal to the xi's. So you'd have x1, x2, all the way down to xn. Cool, cool? All right, so example 8. Find the coordinate matrix of X in Rn relative to the standard basis. So just to show you how this works, the standard basis for R3 is what? Good, it's going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. So these are like the V's in the definition. So V1, V2, V3. So here, if I wanted to write x as a linear combination of these vectors, what would I have? I would have x is equal to 1, -3, 0, but couldn't I write that as 1 times 1, 0, 0 minus 3 times 0, 1, 0 plus 0 times 0, 0, 1. Cool so far? So the coordinate matrix of x relative to the standard basis S is just what? 1, -3, 0, because those are the C's. So my C1, C2, and C3 are here. And that's what we put in here. Cool, cool? All right. Next up, example 9. Given the coordinate matrix of x relative to a non-standard basis B for Rn, find the coordinate matrix of x relative to the standard basis. Okay? Whew! What do I need to do here? Well, let's, say that this here is vector V1, vector V2, V3, and V4. And we're in R4, okay? So remember that, what do we want to do? We want to write x in terms of C1 times V1 plus C2 times V2 plus C3 times V3 plus C4 times V4. Cool so far? Well, I already have my coordinate matrix to this non-standard basis B. So x would equal to -2 times V1, which is 4, 0, 7, 3, and then plus 3 times 0, 5, -1, -1, plus 4 times -3, 4, 2, 1, and then plus 1 times 0, 1, 5, 0. So all I did here is C1 was -2, C2 was 3, C3 was +4, and C4 was 1. Cool so far? And then, the other ones are the vectors in that basis B. So, well, what should I do? I can just multiply this, right? Multiply the scalars and then sum. So, what are we going to have? This would end up being -8, 0, -14, -6, plus 0, 15, -3, -3, plus -12, 16, 8, and 4, and then plus 0, 1, 5, 0. And then combining the vectors, I'll have -20, 32, -4, and then -5. Cool, cool? So for our next example, find the coordinate matrix of x and Rn relative to the basis B prime. So we've been given this basis B prime, and we're in R2. So it's -6, 7, 4, -3. And we've been given that the coordinate matrix of x relative to the standard basis is -26, 32. Cool so far? So if this is my vector v1 and vector v2, what should we do? Well, x needs to be written as a linear combination of the vectors in the basis b prime. Right? Well, I have x, do I not? So here I would have x negative 26, 32 is equal to c1 times v1 plus c2 times v2. So the one before, okay, we knew the coordinate matrix of x relative to this basis b. So we basically knew our CIs, right? Here we know the coordinate matrix x relative to the standard basis. And now we want to know, well, what is this coordinate matrix of x relative to this non-standard basis b prime? And our CIs are unknown. So what do? We would have what? Negative 26, 32 equals negative 6c1, comma 7c1, bringing the c1s in, plus 4c2, comma negative 3c2, and then getting one happy matrix on the right side, what would we have? Negative 6c1 plus 4c2, comma 7c1 minus 3c2. We've done stuff like this before. We're just finding something new. So our system would be what? Negative 6c1 plus 4c2 has to equal to negative 26. And then 7c1 minus 3c2 has to equal to 32. Cool so far? So, solving that system, what would we have? We would have negative 6, 4, negative 26, 7, negative 3, and 32. And so if I did 7 row 1 plus 6 row 2 for a new row 2, I would have negative 6, 4, negative 26. And then my new row 2 would be 0. That'd be what? 28 minus 18 is 10. We'll get 10 here. So what will I have? My system will be negative 6c1 plus 4c2 equals negative 26. And then what would I have? I'd have 10c2 equals 10. So that's going to give us c2 equals 1. And if c2 equals 1, then negative 6c1 plus 4 would be negative 26. So then we'd have c1 would equal to 5. Groovy? So the coordinate matrix of x relative to b prime is equal to 1, 5. Cool, cool? All right, so let's talk a little bit about what's going on. The matrix P is called the transition matrix. From B prime to B, where the coordinate matrix of x relative to B prime is the coordinate matrix of x relative to B prime. And this notation here is the coordinate matrix of x relative to B. Multiplication by the transition matrix P changes a coordinate matrix relative to B prime into a coordinate matrix relative to B. So let's just kind of scope out some of this stuff. So here, a change of basis from B prime to B would be P times the coordinate matrix of X relative to B prime equals to the coordinate matrix of X relative to B. Now, it turns out P is invertible, and so if you multiply both sides on the left by P inverse, you end up with P inverse times the coordinate matrix of X relative to B is equal to the coordinate matrix of X relative to B prime. So that's if you want to go from B to B prime. So let's look at what we were doing. All right, so we had negative 6c1 plus 4c2 was equal to negative 26, and then 7c1 minus 3c2 was equal to 32. Cool so far? Remember in the problem that we were given that the coordinate matrix of X relative to the standard basis was equal to negative 26, 32. So here we go. If P is equal to, so you do your column of C1s, right? And you'd have negative 6, 7. Your column of C2s, you'd have 4, negative 3. And then we multiply P times the coordinate matrix of X relative to B prime is equal to the coordinate matrix of X relative to the standard basis S. What would we have? Well, the coordinate matrix of X relative to B prime would equal to P inverse, right? I multiply on the left by both sides by P inverse times the coordinate matrix of X relative to S. And remember our shortcut for inverse of a 2 by 2 is going to be what? 1 over the determinant, right? So the determinant of P is going to be 1 over, well, the determinant is the denominator, so we'd get 18 minus 28 in our denominator, and then you switch the diagonals and you put opposite signs on the other entries. And then we still have to multiply that by the coordinate matrix of X relative to the standard basis S. And that, remember, was negative 26, 32. So that will equal to, what will this be? Negative 1/10. And I'll go ahead and do the matrix multiplication. That'll be 78 minus 128 will be negative 50. And then we'll end up with, beautiful, negative 10 in the second one. And then when I multiply that negative 1/10 through, I'll just get 5 and 1. Isn't that groovy? So just the same problem done a slightly different way. Okay. All right. So the inverse of a transition matrix. If P is the transition matrix from a basis B prime to a basis B in Rn, then P is invertible, and the transition matrix from B to B prime is given by P inverse. Cool, cool? Now, here's a little FYI for you. It turns out that the transition matrix from B prime to B is P. And that'll be useful in some of the coming problems. So here's a lemma for you. Let B equal to the set of vectors v1, v2, all the way down to vn, and B prime equal to u1, u2, all the way down to un, be two bases for a vector space V. If v1 equals to c11u1 plus c21u2 plus plus cn1un, and then it would go like this. Then the transition matrix from B to B prime turns out to be Q equal to, and what are these made up of? Beautiful, the column matrices. I mean, do you see that C11, C21, Cn1 from that first vector V1? Those are all entries in the first column. And then in V2, the C12, C22, those are all entries in the second column. And so it turns out you can make up these things up of the column matrices, right? And notice you have an n by n. Okay, so transition matrix from B to B prime. So let B equal to V1, V2 down to Vn, and B prime equal to U1, U2 down to Un be two bases for Rn. Then the transition matrix P inverse from B to B prime can be found using Gauss-Jordan elimination on the n by 2n matrix B prime B as follows. You row reduce the matrix B prime B to In, and then what will happen on the other side is you'll have P inverse. Okay? Note the transition matrix from B prime to B can be found using Gauss-Jordan elimination on the n by 2n matrix BB prime as follows. Row reduce BB prime to INP. Okay, so what I do is I just see what's going to be the easiest one. So in this one here, we have a B and a B prime. Remember, we want, at the end of the day, we want the identity matrix on the left, right? So here, what do I do? Well, if I do the B prime first, what do I have? Well, I have the standard matrix, right? So I have 1, 0, 0, 1. And then I have what? 1, 1. And then 1, 0 is going down when I was saying these. So what is this? Well, the left one is IN. Since I put the B prime first, what is the second one going to be? Beautiful. P inverse. So our transition matrix is P inverse, and that's equal to, going across now, 1, 1, and then 1, 0. Groovy? Okay, next example. Find the coordinate matrix of P relative to the standard basis for P3. All right, so, okay, this time I've got a polynomial again. What is the standard basis for P3? Do you remember? Beautiful. The standard basis for P3 was 1x, x squared, x cubed. Cool so far? So if I call this one V1, V2, V3, and V4, what do I have to do? Because what do I want to find? Well, I want to find all the CIs, right? So C1V1 plus C2V2 plus C3V3 plus C4V4 would equal to our P, right? Our vector P. So, what do we have? Well, we'll have C1 times 1 plus C2 times x plus C3 times x squared plus C4 times x cubed would equal to, I'll do it in ascending order, so we'll have 13 plus 114x plus 3x squared, and we don't have any cubed terms, so I'm going to just say plus 0x cubed. Cool so far? So, well, what do? I need to match up the coefficients. So 1c1, right, has to equal to 13. And then C2 has to equal to 114. C3 has to equal to what? 3. And C4 is going to equal to 0. So easy, it's hard, right? I mean, couldn't I have just written P as 13 plus 114x plus 3x squared plus 0x cubed, and then I would have found it because I wanted to find it relative to the standard basis. So the coordinate matrix of P relative to the standard basis will just equal to 13, 114, 3, and 0. Groovy? All right, and that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe. Tell your friends. Bye.